All right, folks, so let's figure out what the pH of this particular solution is at the equivalence point. So just to remind you, at the equivalence point, the number of moles of acid equals the number of moles of base. And so we're talking about taking this acetic acid solution, reacting it with the sodium hydroxide that we're titrating it with, and we're talking the equivalence point. So remember, our acid was 0.5 molar, which is a half, times 30. That gets us the 15 millimoles. So let's put that here. Now, it doesn't say how much sodium hydroxide we're adding, notice, but remember this basic fact. The number of moles of acid will equal the number of moles of base at the equivalence point. So the amount of hydroxide is also going to be 15 millimoles. Well, initially these concentrations would be 0, and so things will change. That will drop by 15. That will drop by 15. The anion will go up 15. The water, I don't know why I just did that, because we know we don't care about that. But anyway, the water would go up 15 as well. So notice no weak acid left over. No strong base left over. Notice we've got anion. We've got conjugate base. That's 15 millimoles. Now, you are not going to like this at all, and quite frankly, I don't enjoy these particular problems either. But what we don't know is how much of the sodium hydroxide solution did it take to get us these 15 moles. So now what we have to do is figure out, well, what is that concentration? And I'll point out why in a moment. So remember, it's 0.5 molar. So we got to know, well, how many milliliters would it take to get us this 15 millimoles? So I'm going to set up a proportion. So 0.5 moles of sodium hydroxide for every 1 liter, or maybe I'll do 1,000 mils, that might make sense, for every 1,000 mils, equals, now remember this is millimoles, so I'm going to convert that back to moles because this is in moles. So that would be, remember, kangaroos hop daily but don't catch mice. So I'm just scooting that decimal 3 to the left. So that'd be 0.015 moles for every X milliliters. So now we multiply 1,000 by 0.015 and then divide by 0.5, and that'll tell us how many milliliters of this particular sodium hydroxide solution there must be. So 1,000 times 0.015 divided by 0.5. So I'm getting 30 milliliters, which makes sense. I kind of didn't have to do that math, but sometimes based on the numbers we get, now notice 15 milliliters brought us to the half equivalence point. Well, isn't it logical that 30 milliliters would bring us to the equivalence point? So now we know we've added 30 milliliters of sodium hydroxide. Quite frankly, this math is unnecessary in this problem, but I wanted to set it up so that you could see what you're doing when you end up with much wackier numbers than simply 0.5s, right? As you know you will. So now we know that we started with 30 mils of acid. We know we must have delivered 30 mils of sodium hydroxide to get us to the equivalence point. So 30 mils plus 30 mils, now we know we've got 60 mils. So our concentration, the molarity of the of the anion at this stage is 15 millimoles divided by 60 milliliters. The millis cancel out, and we're left with 0.25 molar, because 15 divided by 60 is a quarter. Now, you might be saying, but wait a minute, that's not the pH, and I hope you're realizing that. Because now, what we have to do is this. And I told you weren't going to like this. But this is a weak acid, we have none left. This is strong base, we have none of it left. All we've got is conjugate base. And so this conjugate base is, and water, this conjugate base is what's determining our solution's pH. So now I have to treat that conjugate base as a base, which means I'm going to react it with water, because you might remember I was asking these dumb questions like, hey, bases end in OH and have OH, and I was pointing out the pH square. Well, remember, there is no OH in acetate. So this is where we have to react it with water to form hydroxide. So notice by reacting it with water, the water is the acid, the conjugate base is base, and so we end up with hydroxide. Well, now we know the initial concentration of the anion is 0.25 molar. Who cares about water? That'd be 0, that'd be 0. This will change. This is going to be weak. We're going to take a minute in a moment to figure out what the Kb of this particular compound is. But whatever we end up with, it's going to be less than 1, I can assure you. Look at its acid's Ka value, 10 to the negative 5. So just to remind you, Ka times Kb equals Kw. So we know the Kb of this is going to be small. I'll prove it to you in a minute. So this is going to drop by x. Who cares about water? This is going to go up by x. This is going to go up by x. So now at the end, we've got 0.25 molar. That x is practically 0. Water, who cares? Acid, hydroxide. So that's step 1. Basically, we're just walking through the 5-step procedure to figure out what is the pH of a weak base. The second step is to write the Kb expression. Kb would be Ha times OH over anion. We ignore water. Step 3 is to plug in values. So back to this, I've got to figure out what the Kb value even is. So Kb would be Kw over Ka. So the Kb is going to be 10 to the negative 14 divided by 1.8 times 10 to the negative 5. What you might be saying, where did that come from? From right here. I just brought her on down. Now we're using it in this problem to find the Kb. So 10 to the negative 14, just plug that into the old calculator. 1 times 10 to the negative 14 divided by 1.8, 10 negative 5. And we get the 5.56, something we've done before. So we know the Kb equals 5.56, 10 negative 10. The Ha and the OH, according to our ice table, is x squared. The anion is 0.25 molar. So now it's just a matter of algebra again. Multiply by 0.25 on either side and square root. And so we end up with x is the hydroxide, which equals so hopefully I hit the buttons right. It looks right. So I'm getting 1.18 times 10 to the negative 5 molar hydroxide. So that's our third step. That's a very important part. Remember, what we're trying to do here is the pH and determine that. So now the fourth step would be to negative log. So if I didn't have a calculator, I know, being that this is 10 to the negative 5, I know that the negative log of that is going to be approximately 4. In fact, very close to 4. Very close to 5, because this is almost 1. So I'm going to negative log that now. And I end up with 4.929 as a POH. And then remember, the pH is simply 14 minus that. So I subtract that from 14, and I end up with the pH being 9.071. Remember, that should make sense. We started with an acid, just straight up weak acid. The pH is 2.523. Then we added some sodium hydroxide. We got to the half equivalence point. The pH went up to 4.745. We added more base, brought us to the equivalence point, and that pH should be 9.07. And so just for those of you who might be thinking, but wait a minute, I thought we've got equal number of moles of acid and base, but yes, And if you're thinking, but wait a minute, if we've got the same number of moles of acid and base, shouldn't we have a pH of 7? But think about this. Haven't we made, by reacting weak acid with strong base, haven't we made a basic salt? And so if we've made a basic salt at the equivalence point, shouldn't our pH be above 7 anyway? And that's what we've just established. So I'm going to let you ponder that, get something to drink, take another bite of food, and then we'll dig into what is the pH once we've added even more base, and then which is going to be an easy problem for us again, and then we'll look at what the titration curve of this looks like. See you in a minute.